now going to look at another thermodynamic quantity, and we refer to that quantity as Gibbs free energy, or we symbolize it by delta G, and sometimes we just call it free energy. And we'll see that we can use this equation to calculate whether or not a reaction will be spontaneous. So Gibbs was a mathematician. I believe he was awarded the first PhD in America. Graduated from Yale in 1863. He's a smart mathematician, and he just proposed this equation. So delta G is Gibbs free energy. Delta H is the enthalpy change. So we've talked about that quite a bit. And remember, if delta H is negative, that is favorable. The universe likes to go downhill in energy. So downhill in energy is good. So a negative sign for delta H is favorable. And then the entropy change, we've spent a little bit of time talking about that. And if the delta S is positive, if that term is greater than 0, then that's favorable. The universe likes to go from order to disorder. And so if we just consider this equation and look at the sign here, and also make sure that the temperature is always in Kelvin, so that value will never be a negative number. If delta H is negative, then we've got a negative sign here, so a negative number minus, and then if T has to be positive, if the entropy change is positive, oh, I should have put the H here. So we have a value here. If delta H is negative, and we subtract off a positive term here, so a negative and another negative, so that's another term, then again this is favorable. We have a negative delta H, and a positive delta S is also favorable. This negative sign here in the equation means that the sign of delta G would also be negative. So when that's the case, if delta H is less than 0 or negative, and delta S, or the entropy change, is greater than 0, then delta G will always be a negative number at all temperatures. So we don't even really have to do a calculation to see if our reaction would be spontaneous. So a negative sign for delta G is also favorable. So if delta G is negative, then our reaction, delta G, yeah, so that means, so the reaction is spontaneous at all temperatures. So there would be no temperature where that reaction would go from non-spontaneous to spontaneous. Both terms are kind of in a line with the way the universe wants to go. So this very famous equation, we'll be using this quite a bit because these are capital letters. This is another state function, and so there are a variety of ways that we can get to the answer, and we'll always get the same answer. So the state function, remember, means that no matter what the path is that we take, we're always looking at the difference in the final state minus the initial state. Okay, so we'll be actually calculating delta G values from thermodynamic tables that are usually listed at the end of a chemistry book or in the CRC handbook of chemistry and physics. So we'll be looking at some example numbers there. And so this equation here, if we have a positive delta H, so that would be, if we just look at that, I'm going to rewrite write this equation, delta G equals delta H minus T delta S. So let's say that the delta H term was actually positive. So this is for an endothermic reaction. This is not common. This is going uphill in energy. So this is not favorable. The universe generally does not go in that direction. It doesn't go uphill in energy. So if this is the case, if delta H is greater than 0, and if delta S was less than 0, this is also not favorable, because the universe goes from order to disorder. So a decrease in entropy, remember, means a decrease in disorder. And if you don't need to look very far to know that that's the case. The top of your desk goes from order to disorder without you having to do a whole lot. In any case, in this situation, if we just look at the math here, delta H is greater than 0, then we'll have a positive value here, minus T. T can't ever be negative, so that minus sign is part of the equation. And if delta S is a negative number, T is going to be multiplied by another negative. So we have a positive minus a negative, or in that case, this turns into a positive plus a positive value. So our sign for delta G would be positive. So a positive delta G means the reaction is not spontaneous. And in this particular case, this was true. Both terms, the energy term and the disorder term, were not favorable. Then this reaction would never be spontaneous. So this reaction is never spontaneous, no matter what the temperature is. Never spontaneous at any temperature. In fact, the reverse reaction would be spontaneous. And what we're getting ready to do is look at a case where we have competing terms. Yes. Okay. So these are kind of like the two extremes. So a favorable energy change and a favorable disorder change, then that reaction is definitely going to proceed and be spontaneous. So a negative delta G means spontaneous, and a positive delta G means not spontaneous. And the reason we care about this is we can make a lot of money, or at least we could maximize our profit, if we are running a reaction that is automatically spontaneous. That means we don't have to add in any energy into that reaction for that reaction to occur. So oftentimes we have two competing terms. So if delta H was less than 0, that's favorable. But delta S was greater than 0, that's not favorable. Then the temperature that the reactions run at will affect how big this value is here. So then we would have a competition between the terms. Then the temperature term, well, then there would be a competition. And the temperature would affect whether or not the reaction was spontaneous. Spontaneous. Okay. Or we could also have the reverse. We could have a negative delta H, which was good, and a negative delta S, which was bad. or not favorable. So we may have these two terms competing. And so the sign convention, whether something is positive or negative, is going to be a big deal. So what I'm going to do is we're going to analyze the free energy of the reaction that we've looked at several times, which is the Haber process. And so we've already looked at that and decided what we think about the entropy change. So if we consider this reaction, 3 moles of hydrogen gas and 1 mole of nitrogen gas, this is a reaction that comes to equilibrium, and that is the process for making ammonia. And we looked at this and we decided that the delta S term is less than 0. So this is not favorable, or an easy way to say that, I'll just say it's bad. So nature is not going to proceed in that direction from disorder to order. Here we have 4 moles of a gas on the left, going to 2 moles of gas on the right. So this side is going to have more order because there are less things to create disorder. So this side of the equation, or the product side, has more order than the reactants side. Okay. So the delta S term is bad. This is also known as an exothermic reaction. So we're getting ready to calculate a value for the entropy change as well as an exact value for the energy change. But for now, we'll just look at this. If heat is produced during this reaction, then that means our delta H term is negative, so that's good. And this is often the case. One of the terms is not favorable or bad, and the other term is favorable. So what we're going to do is calculate the value of delta S from the thermodynamic tables, and then we'll calculate the value of delta H. We'll assume that we're going to do this reaction at 25 degrees Celsius, and we'll calculate each term, plug that into this equation with the temperature in Kelvin, and then calculate the value of delta G, or the Gibbs free energy. Okay, so let's do that one. What I'm going to have to do first is show you a table, and if you have a textbook, then you would probably find a table similar to this in the appendix. So I've added a few. I just found this information. And so delta H, this is the heat of formation, and let me see, let me just zoom that in here. Zoom in on that for a minute. And focus this a little better. That's helping me. We've got the delta H. This is the heat of formation. This means we are at standard conditions. And this is the formation of 1 mole of a compound from the elements. And then we see a delta G, which is another thermodynamic quantity, and then S. So we're going to have to pay attention to our units when we do the calculation. But these values are going to be the same no matter what book you look in, because these are not made-up values. These are actual thermodynamic values. And so this is a very short list of a few things, and I've added nitrogen and ammonia to this so that we would have numbers to work with. Now, let me zoom back out of here. Actually, it's pretty good right there. Just stay right there. Okay, so I'm going to be using values from this table, and we're going to calculate delta S for the reaction above. And we always take delta S, means S final, minus S initial. So for us, this is always the entropy of all the products minus the entropy of all the reactants. So we have to be careful how we do the arithmetic with these numbers. So if we look at, we've got two products over here, 2 moles of NH3. So if I write this, this is 2 moles of NH3, and then we're going to multiply by the entropy value in the book for NH3. And those are the only 2 products. So I'm going to subtract off the entropy for nitrogen and subtract off the entropy for 3 moles of hydrogen. So subtract, and we have 3 moles of hydrogen, and we're going to multiply that by the entropy value for hydrogen, and then I'm going to subtract off the 1 mole of nitrogen and multiply that by the entropy value. Yeah, we don't really need to write all this out. So all we have to do is look at the value for NH3 and make sure that we multiply it by 2. But this first time I do this, I'm going to go ahead and write everything out. Just quit moving. Okay, so the entropy value for NH3 is down here, and notice entropys are always going to be positive in these tables. So the entropy for NH3 is 192.5. That's joules per Kelvin per mole. So 192.5 is what's going to go here. So we have 2 moles and then 192.5 joules per mole per degree Kelvin minus 3 moles of hydrogen. So the entropy value for hydrogen is over here, 130.58. Make sure we got the right number there. This is 130.58 joules per mole per degree Kelvin. And we're going to subtract off the 1 mole, and the entropy value for nitrogen, I had to write on here, is 191.5. 191.5 joules per mole per degree Kelvin. And I wrote all of these units out so that we could see that the moles are going to cancel. So all we really have to do when we use the thermodynamic data from the back of the book is just look at the formula, make sure it's in the correct state, and then multiply by the number of moles. So the unit for entropy is always going to be a joule per Kelvin. So we do this. And we just got to be careful that we do the math correctly. 2 times 192.5 minus 3 times 130.58 minus 191.5. And when I do put those numbers in, I get a negative. So the delta S, put that right here, delta S for this reaction is negative 198.24. And the units for delta S, that is an energy unit per Kelvin. So we just use the back of the book. This also confirms what we saw just by looking at the reaction. We predicted that since we have 4 moles of a gas going to 2 moles of a gas, that the reaction is going to, oh, I should have said, oh that's right, less order, more order. Yeah. So this is less disorder. So entropy is really in terms of disorder. I confused myself there. But we have less disorder with 2 moles than we would for 4 moles. So we already looked at the reaction and said less order means we're going to be going, our change in entropy is going to be negative. Now we're going to calculate delta H. So We'll calculate the entropy change. And we're assuming, which I did not write down, that we are doing this reaction at standard conditions. So it's 25 degrees Celsius, 1 atmosphere pressure for any gases. So we can use those values in the back of the book. So now delta H, I'm going to take 3 times, and have this exact same setup, but I'm going to look at the delta H value for NH3. And then the heats of formation for elements are always 0, so we'll see that. So the enthalpy column is the first column. So the heat of formation of 1 mole of ammonia is negative 46.19, and that's in a kilojoule per mole. So my delta H is going to be 2 times negative 46.19. That's a kilojoule per mole, so that mole, cancel the kilojoule per mole. Again, you really don't need to write that. And I'm going to subtract off 3 times the delta H for hydrogen minus 1 times the delta H for nitrogen. If you recall from earlier classes, the heats of formation for elements are going to be 0. And we can see that here. Hydrogen, the way hydrogen occurs as an element, is in the diatomic molecule H2. There's the element O2, the element N2. So the delta H value for those are always going to be 0. So I subtract off 2 zeros. So my delta H value here is negative 2 times 46.19. This turns into a negative 92.38 kilojoules. So our delta H value is negative. That's favorable. This is an exothermic reaction. So I'm tired of writing out that long word favorable. I'm just going to say good. Our delta S value was negative. That is less disorder, which means more order. That's bad. That's not favorable. So we have 2 competing terms here. So when we plug this in and solve for delta G equals delta H minus T delta S, we won't know that the reaction is spontaneous until we look at the sign of delta G. So if we plug in delta H, negative 92.38 kilojoules, minus our temperature, 25 degrees Celsius, is 298 Kelvin. So we've got to convert our temperature to Kelvin. So minus 298 Kelvin, and our S term is in joules. So we can't add a kilojoule to a joule. Whenever we're adding or subtracting, we have to have like terms. So I'm going to change my delta S value up here to be negative 0.19824 kilojoules. So to go from a joule to a kilojoule, we move the decimal 3 places to the left, which is the same as multiplying by 1,000. There's 1,000 joules in a kilojoule. So our delta S term now is in the correct kilojoule units. So now we're going to multiply that by a negative 0.19824 kilojoules per degree Kelvin. So the Kelvin unit cancels. So our delta G is this number, negative 92.38. And I'm going to subtract off minus 298 times negative 0.19824. So if I put all that in correctly, we get negative 33. So the units for delta G are also going to be in kilojoules. So we do this and we get negative 33.30 kilojoules. There's an easier way to do this calculation, and we'll do that in just a minute. So this is spontaneous at 25 degrees Celsius. And if we ran this reaction, we could get the maximum amount of work we could get out, maximum work that this reaction could do for us is 33 kilojoules. So not only does Gibbs free energy value, the sign tells us whether or not it's spontaneous, but the more negative this term is, the more work we could get out of that reaction. Another way to calculate delta G is using the delta G column that's in the table of thermodynamic values and doing the same thing we did up here. We have 2 moles of NH3, so if we multiply that by the delta G value and then subtract off all the reactants. So delta G is 2 moles of NH3 times the delta G value for NH3 minus, and just to save time, I'm going to tell you, and we'll see it in the book, that the delta G values are just like the delta H values for elements. They're equal to 0. And we're going to be able to see that. So I'm going to take this delta G column, which is the middle, and for NH3 it's negative 16.66. Nitrogen has a delta G value of 0, and so does hydrogen. So delta G is going to be 2 times negative 16.66 kilojoules per mole, but that's also a mole. So I end up with just kilojoules. And we get a very close value, 33.32. That sign makes it negative. So that's the beauty of a state function. No matter what we do to do the calculation, we'll get the same answer. So using the table is a much easier value than actually solving for delta S separately and then solving for delta H separately and then plugging those values in. There is a time when we would do that, and that would be in a case similar to this, where we have 2 competing terms. The delta S term is unfavorable. The delta H term is favorable, wherever that is, right here. So we might solve for the temperature at which the reaction goes from spontaneous to non-spontaneous. But otherwise, if we're going to calculate delta G, we should just go straight to the table and do the sum of all the products minus the sum of all the reactants.